In 2015, NASA announced its Artemis program. Artemis is part of a big effort by NASA to revitalize the United States space program. The big picture is to be able to reach and complete missions on Mars safely. However, in order to accomplish this, consistent and safe missions to the moon must be completed first. To develop the space program, Artemis is inspiring new and young engineers to begin and develop their skills in the STEM field. Part of this effort is sponsoring competitions such as the Lunabotics Robotic Mining Competition. This year, the UIC team that is competing in this year's competition consists of Brian Domke, Jonathan Garcia, Matt Myers, Adrian Rahaja, Marissa Munya, and Joe Stiso. The goal of this competition is to design and create a lunar rover that is capable of navigating through a simulated lunar environment to a designated area where the robot will dig and excavate at least 30 centimeters into the ground.
The NASA Robotic Mining Competition requires a digging mechanism and mobility system. Some completed rovers from past competitions are shown. However, the scope of this project only includes the digging mechanism for the rover. The goal is to design and fabricate a digging and filtration mechanism and attach it to UIC's engineering design team's mobility system. The team will earn 1,000 points if the rover passes safety and communications inspections, and the rover fits within the starting dimensions shown in the figure. The team will also earn 10 points per kilogram of gravel mined in excess of 1 kilogram. To do this, our mechanism must dig through 30 centimeters of regolith to reach the gravel layer, and must dump it into a collection bin at a height of 50 centimeters. The team loses 8 points per kilogram of mass for the rover. Dust-tolerant design and dust-free operation will earn points according to the judge's discretion. Automation of the digging and dumping process earns 50 points each. The team will also lose points for camera and data bandwidth used along with energy consumed.
After reviewing videos of various digging mechanisms from the previous NASA competitions and studying written works on the topic, the team narrowed down the design for the digging mechanism to be based off of one of the 4 following systems. These 4 systems consisted of an auger, a bucket ladder, a bucket wheel, and a scooping arm. The main reasons why these 4 stood out from other digging mechanisms were due to the fact that all 4 have had some form of proven success in this competition previously, while also appearing to be the most feasible to manufacture with the tools available. The team used a design matrix to assist in selecting the digging mechanism type that would be the most optimal for this specific application. 7 key aspects were considered for each design type, and scores were given at the discretion of the team members. As is displayed in Table 1, the selection criteria related to the mechanism's overall mass and mining capability were ranked at the highest weight of importance. This is due to them both being directly related to how Chicago EDT can earn competition points. Other criterions such as simplicity and initial dimensioning were also taken into consideration in order to make the design and fabrication more feasible. Out of the 4 designs, the 2 most prominent options were the auger system and the bucket ladder system, with the bucket ladder scoring the highest overall. Some key factors that made the bucket ladder stand out from the competition were that it scored the highest on all 3 major design criterions, as well as scoring the highest in the initial dimensioning section. Additionally, the team's research uncovered that in previous years, bucket ladder systems have proven to be the most effective in their competition and have outperformed their auger mechanism competitors. The team's digging mechanism will also have an additional filtration and dumping system for unloading the collected mining sample. This simple system consists of a mesh collection bucket and 2 linear actuators that pivot on a rotational point. This allows for the team's mechanism to do all 3 actions of digging up a sample, filtering the sample, and then finally unloading the sample into a sieve. The 2 biggest challenges for the team when designing the bucket ladder mechanism were the digging depth requirement and the size constraints. To overcome the digging depth issue, the team decided to design a bucket ladder that extends and retracts using a linear actuator and constant force springs. The size constraint concern was addressed by designing a bucket ladder with a bend that allows for the shape of the bucket ladder to be adjustable.
For our preliminary calculation, we need a solid idea of how much space the gravel collected is going to occupy. Since the goal is to collect 5 kilograms of gravel, the following calculation is telling us that our collection bucket needs to have at least 235.2 cube inches to accumulate that amount. An important aspect the team focused on is getting a filtering method that is able to separate regolith. To achieve this, we are testing different metal masks with different hole sizes, as well as 3D printed mesh. We were able to filter the gravel well with mesh sizes that ranges from 1/4 to 5/8 of an inch. Additionally, with an angle of elevation ranging from 9 to 15 degrees on a smooth metal surface, we found that this gives us the optimal gravel sliding. Since our dumping sieve is placed at a higher position, it is important that the team devise a plan to dump the content of the collection bucket into the sieve. We decided to use 2 linear actuators mounted into the frame, such that when they extend, they will lift the collection bucket to an upright dumping position, as shown in the picture. We calculated the weights and position for these different lengths of linear actuators, and we found that a couple of 12-inch 150 pound force linear actuators are going to give us the lift that we need. Moving forward to our digging mechanism, the first thing we did is find out the amount of torque needed to operate our digging mechanism. Our team did a calculation based on the weight of the component of the digging bucket, the distances of the tensioner wheel, and the diameter of our gear to find the minimum amount of torque needed to operate the bucket ladder.
In the digging mechanism, the constant force springs are used to retract the belt of the bucket ladder once it is finished digging. To select the proper constant force spring, the load, such as the mass of the belt and gravel, on the spring, and the extension length required were considered. A finite static structural analysis was performed on the digging buckets that will be attached to the belt of the bucket ladder. The size, shape, and thickness of the digging buckets were considered in the simulation. We plan to manufacture the buckets out of stainless steel sheet metal. An additional analysis was also done for the frame of the rover. This was performed to ensure that the rover could handle the load of the digging mechanism and gravel that will be collected during competition.
After reviewing the calculations and testing, parts were specified and chosen. First is a brushed DC motor with a stall torque of 2,420 millinewton meters. Next is the linear actuators used for the digging extension, which have a max extension of 14 inches with a force of 450 pounds. The linear actuators used for the dumping are capable of extending 12 inches with a max force of 150 pounds. The buckets that are attached to the belt are made of 301 stainless steel with a thickness of 0.015 inches. Finally, the mesh used to filter the gravel has a diamond pattern opening of 0.04 inches by 0.091 inches. As mentioned previously, a traditional bucket ladder design did not meet the team's key requirements, therefore significant modifications were made to the design. The operation goes as follows. The digging motor is activated. The front digging actuator extends the full 14 inches. Top layer regolith and gravel are collected and then transferred to the collection bin. The regolith and gravel are separated via the mesh. And finally, the dumping actuators extend the full 12 inches until the collection bin is empty.